Hello, AP class. Welcome to a new week. Monday, we are starting off here with some review of the year. So, I wanted to give you a quick little rundown on the background of what they expect for this particular test. So, if you go to the AP website, they have their material broken down into 8 topics. Now, the topic numbers don't necessarily match the units in the order that I taught in. They tell teachers when you go to seminars and different trainings that it's not really meant necessarily to be taught in this particular order that they're presenting it. This is just how they're clumping it together. But they lumber them 1 through 8. So number 1 is atomic structure and properties. 2, molecular ionic structure. 3, intermolecular forces. Chemical reactions, kinetics, thermo, equilibrium, and then acid base and applications of thermodynamics. So the first 7 topics are on the exam, and they have cut off the last 2 topics. So this is some good news for us and maybe some bad news. I don't know, depending on how you interpret things. The acid base, I would think most people are probably pretty happy that that's not on there. They're cutting out a lot of the major difficult subjects within acids and bases. There's one thing though that is a little confusing to me, and I think that we do need to actually know a little bit of acid base, is when you go and you dig down into these previous topics here, they introduce acids and bases in this one. They also introduce titrations. So when we're studying, I would say that for the most part, we don't need to know acids and bases in terms of really complex stuff like pH and buffers and things of that nature. But I think that you should be able to, dang it, sorry about that. You should be able to use the Bronsted-Lowry definition to identify your acids and bases. And I think that you should be able to do a titration. So I'm not 100% sure on that, but I personally would be able to do those things. And so when it comes to identifying acids and bases with the Bronsted-Lowry, remember that acids donate H's and bases accept them. So that one shouldn't be bad. They also introduce redox reactions here. So you should be able to look at something and decide if it's being oxidized or reduced. But for some reason, we see down here in Unit 9, applications of thermodynamics. Now, applications of thermodynamics, for the most part, I always interpret that as things like entropy. So delta S and delta G. But this is also where they stick the electrochem. So you still need to know redox reactions up here in the types of chemical reactions. I'd be able to balance them. I'd be able to see what's being oxidized, what's being reduced, track electrons. But as far as voltaic cells and electrolytic cells and electrolysis, being able to calculate, how much is plating out of something using the Coulomb's, the Faraday's constant, all these different things, none of that's going to be on there. So to me, that's a little bit of a downside. I thought you guys did really well with the electrochemistry and making batteries and using salt bridges and things like that. So I'm a little bummed that the electrochem's not on there, but they're leaving it off. So if we were to go through these really quick, if you're trying to find a place to look, for the most part, you will find that their Unit 1 material is our Unit 8. So this is mostly Unit 8 for us. Molecular and ionic structure is basically like bonding and things of that nature. So this is Unit 9 for us. And then there's also, we did a little bit in Unit 11 with our alloys and things like that would fall in here. The intermolecular forces we know that that was unit 11 for us most recently, but they also put all of the gas law stuff here. So this is going to be unit 2 was all of our gas law stuff. Chemical reactions was unit 7 for us. Kinetics was unit 3. Thermodynamics was unit 5. And equilibrium was lumped with thermodynamics for us. So that would be unit 5 as well. So these are really the main units that we're going to be looking at. So today, what I wanted us to focus on, basically what we'll do is each day we're just going to kind of cover one of these things, give you guys a real quick rundown on it. I would recommend, though, that if you really want to be thorough about this, is look back at the Unit 8 material, and you will remember that we had an objectives lists, and we had a review worksheet. That is a really quick way to study everything from Unit 8. It's still up in Classroom, so it should be pretty easy for you guys to just flip back and see it. So you have that available to you for each one of these. So you basically have like a little 2-page study guide for each one of these units. What we're going to do, though, is make sort of a master cheat sheet here. So on the test, you're going to be using this, right? We need this for all of our equations. It should get us everywhere we need to go really quick. And so we're going to look at this first topic 1 is the first value that we have up here, and that is the atomic structure, our Unit 8. So when we're looking at this type of thing, we're going to zoom in here a lot. Well, first off, in atomic structure, that's where we talked about, protons, neutrons, electrons, and the structure of the atom. And then we talked about light, how light is created, and we had these 2 light equations. And so they give us all the data for those light equations over to the side here. So we see the constant for light, and we have Planck's constant. So we don't have to look all that stuff up. It'll be right there in front of us. But some other things from that topic that we should be aware of. This is where, if you dig down into their material, this is where they say that you should be covering moles, the concept of the mole and molar mass, which shouldn't be an issue for us. But one thing that some people might have forgotten is the mass spec. So we've just recently used the mass spectrometer. Also percent composition. This was where we did electron configurations. This is also where we did photoelectron spectroscopy and trends. So let's just take a quick look at each one of these things. I think the mole and the molar mass, we don't really need to spend too much on there. But the mass spectrometer, we've just recently looked at that. Pretty complicated in terms of helping to figure out complex molecules and what they might be fragmenting into. But don't forget, way back in the day with the mass spec, when we first started using the mass spectrometer, it was to find the average atomic mass. And so what you basically had here was a weighted average. The mass spectrometer gives us the mass of fragments, and if we're just dealing with individual elements and isotopes, we could use that to find the weighted averages that we find on the periodic table. So remember, percent abundance times the mass plus the percent of the next isotope times the mass, and you keep doing that for all of the different isotopes, and this gives you your weighted average. Okay, so that's something that we should be comfortable with, is using mass spec data to find weighted averages and such as well. Now, percent composition. Remember that percent composition is a very useful calculation for us. It does a few things for us. It helps us to figure out if a substance is pure, and it also helps us find the empirical formula. Right? So for example, if you have something like H2O, we know that with H2O, you would basically say 2 times 18 point, or sorry, that's the whole molar mass. 2 times, if we're trying to find the percent hydrogen here, you go 2 times 1.01 all over 2 times 1.01 plus 16, and then times 100 gives us the percent hydrogen. So if you are trying to figure out if a substance is pure or not, you would take a sample of that substance and you would say, hey, experimentally, what is the percent hydrogen in this? And if the percent hydrogen did not match the theoretical percent hydrogen from our math here, you know that there must be something else in there that's messing it up. If you have a bunch of different percentages, if you know the percent of each individual compound, remember that you could solve for the empirical formula. And we had a system for that. We said percent to mass, mass to mole, and then divide by small, and then multiply till whole. And so we can find empirical formulas that way. Now, as far as electron configurations go, hopefully you guys are doing okay with those. Remember that we use the periodic table to find those electron configurations. And so abbreviating them is fine. So if you wanted to do something for, let's say, sulfur, then we would say that we would go up a row to the very last column, the noble gas column, and we would say that it's neon. And then after neon, we would have 3s2, 3p, and then sulfur is 1, 2, 3, 4 over. So that would be our electron configuration for sulfur. Now, the cool thing here is we link that right to the PES. PES stood for photo electron spectroscopy. And what this did is it helped us to see these electron configurations, and it helps us with the trends as well, confirming the trends. So what we know is when we look at a PES, if we were looking at a PES for sulfur, remember that we see the peaks, and the peaks tell us their electrons. So you would see a small peak here, and then you'd see another small peak. That's 1s. This is the equivalent of the 1s2, 2s2, and then we would see a larger peak, which would be a 2p6, and then we would see this guy is a 3s2, and then we would see a 3p4. Now this one wouldn't come up quite as far because it doesn't have the full 6. It would be a 3p4. So this would be our PES, and what we would see is that the numbers here would be really big numbers, and then these would be smaller numbers. These are the ionization energies. We know that these 1s electrons are in very close to the nucleus, and so they are going to be held extremely tight, right? And that's from Coulomb's law. So don't forget Coulomb, right? Coulomb said that if things are really close together, there's a really good electrostatic force there, right? So small items or items with large charges. So if these 1s electrons are sitting right next to the nucleus, we know that they're going to be held very tightly, and it's going to have a very, very large ionization energy, which is backed up by our trends here. Because when we talk about the periodic table, remember that the smallest atom on the periodic table, remember we don't count the noble gases in these trends. So we're looking at fluorine. Fluorine is the very smallest, so this would be the smallest radius and the largest ionization energy. Now, when we do these trends, remember, and I'll wrap it up with this. When we talk about these trends, you can't just say they're going to give you different chemicals to compare or different elements to compare. For example, they might say compare oxygen and fluorine. Which one has a smaller radius? You would say fluorine. because you don't want your explanation to be because it is further up and further to the right. That's just an observation, not an explanation. We need to actually tell why this is happening. And so when we make this explanation, you want to talk about a couple of things. Remember, those things were nuclear charge, nuke charge, and shielding. All right, so F and O are in the same row, so they have the exact same amount of shielding, right? The inner electrons are the same. Their valence electrons are all in the same ring. So F, because F has a greater nuclear charge. So since it has a greater nuclear charge, it's going to grab onto those electrons tighter and pull them in very, very close to the nucleus. So we would say, therefore, or let's use the little therefore sign. We'll say, therefore, smaller radius. Ooh, how small can I write? So therefore, we have a smaller radius on that nucleus. Now, if they said, why does F have a larger ionization energy? So if I had to do that, then I would say, oh, well, F has a larger ionization energy because of Coulomb's law, right? Coulomb says larger charges, larger ionization energies. Or, in this case, we would say, since F is smaller, Coulomb's law states it's going to have a larger ionization energy because the particles are closer together, right? So those are the types of explanations. So when we're talking radius, we want to talk about these things here. And when we're talking about things like ionization energy or electronegativity, then we should be talking about Coulomb's law. Remember good old Coulomb. So this has been a quick review of topic number 1, our unit 8. So atomic structure and periodicity.